Hello, everyone, and welcome to a short presentation on our paper on differentiability and optimization of multi-parameter persistent homology. Okay, so let's dive right in and get a bit of background information on single parameter persistence. So this is a tool to analyze discrete data by studying the underlying shape of that data. So for example, here, given this point cloud data on the left, we might want to extract the fact that it seems to be sampled from a circle. So how do we do this? We construct a family of topological spaces. This is usually filtration. In this case, we have a filtration of simplicial complexes. And then we want to kind of use tools from algebraic topology to track how topological features vary across the filtration. So for example, here we might use simplicial homology. And so for example, we can see this circle being formed at time step 3 in the filtration and then getting filled in only at the end. So it kind of persists through a significant portion of the filtration. And the fact that it persists for so long is indicative of it being sort of an underlying feature of that data. And this is the key upside of persistence, is that you look at the entire filtration at once rather than a single snapshot of that filtration. Okay, the nice thing is also that this information for one parameter persistence, that it can be completely represented by something called a persistence barcode. So for each feature, for example, for this circle, you draw a bar that starts at the time it was born, in this case, time step 3, and ends at the time it dies at the last time step here. So you can also think of this as a collection of points in R2 that represents the lifespan of that feature. Okay, so how do we use this for machine learning? Okay, so consider the entire pipeline, starting with data, then constructing your family of simplicial complexes or filtration of simplicial complexes, then computing your persistence barcode, and then defining a real valued loss function. So you can do this loss function in multiple ways. It's pretty easy because there's a metric that you can place on this space of barcodes. So it was proven in 2021 that this pipeline is differentiable almost everywhere, and that stochastic gradient descent converges almost surely to a critical point when you consider a loss function as the composition of this entire pipeline. Okay, so this allows us to incorporate persistence-based loss functions into the machine learning pipeline. So you can use topology, so you're kind of incorporating topological features in your machine learning pipeline. And so there have been many successful applications in fields such as drug discovery, where you're trying to look at the shapes of the molecules, topology preserving autoencoders, among others. And yeah, so our idea is to kind of generalize this framework to multi-parameter persistence. So first of all, what is multi-parameter persistence? Well, you might recall that I just said that one of the key points of persistence is that you're looking at you're looking at the entire filtration at once rather than a single snapshot of that family. But there's often more than one option to filter the topology of your data. And this leads to multi-filtrations. In this case, we have a bifiltration. So on the x-axis, we have the same kind of parameter that we had earlier. You can think of this as sort of growing of different radii of balls that you can grow around each point and then constructing your simplicial complex correspondingly. On the y-axis, you have a Gaussian density estimator. There are other examples that pop up in applications in domains such as drug discovery. You might want to consider molecular bond length and molecular strength, among others. This gives us much more information, these multifiltrations, but due to representation theoretic results, there is no analog to the barcode that can completely characterize the topology of these multifiltrations. This leads to multiple incomplete invariants, which have been proposed in recent years, including Hilbert decompositions, signed barcodes, and Euler characteristic, among others. Okay, so what is our main result? Our main result is a framework that generalizes the differentiability results from the single parameter case to the multi-parameter pipeline. And the main strength of our results is that they hold for a large class of invariants under very mild assumptions. And indeed, we believe most of the, almost or all of the results of the invariants that have been proposed thus far. So what does the pipeline look like? We start off with discrete data. In this case, we have time series data rather than point cloud data. And then you can have your pick of invariants, whether that be the Hilbert decomposition or the signed barcode or the Euler characteristic. And then you do some sort of learnable representation. More often than not, this is just some sort of sign measure. And our framework says that if you look at loss functions defined on this pipeline, they would be differentiable almost everywhere. 2, that stochastic gradient descent converges almost surely to a critical point. And this allows us to then incorporate multi-parameter persistent-based loss functions into machine learning pipelines. So let's just look at one example that we presented in our paper, which is a very visual example. So we want to start off with this data on the top left, which is points on a circle plus a lot of dense points in the middle. And then we want to make cycles primarily using these bunch of points in the center. But at the same time, we want to preserve the outer circle. And the way we do this, we use a bifiltration, radius and density, just as we presented earlier. And as you can see at the bottom right, at the end of the optimization process, we have cycles created in the center while maintaining the outer cycle. And as you can see, the denser points create smaller cycles. And in contrast, the one parameter analog of the experiment, which you can look at in our paper, destroys this outer circle and just creates a ton of smaller, similarly sized circles. So this shows that we are able to preserve sort of the density parameter. So in summary, we've presented a novel general framework to differentiate and optimize loss functions based on multi-parameter persistence. And in our paper, you can find proof of concepts and applications ranging from graph classifications to time series classification, topological autoencoders, and as we just saw, point cloud optimization. Okay, so thanks a lot for listening to the presentation. Feel free to contact us, look at our paper, look at the code base, or drop by to the poster session on Wednesday.